Okay. It's 7 o'clock. Good evening, everyone. Welcome. I'm Mila Stroganoff, your host and facilitator this evening, and the program's director and field trip director for the Friends of San Pedro Valley Park. Please check the Friends website for recorded natural history webinars and activities pertaining to the Friends of San Pedro Valley Park in Pacifica. And our website, as you probably all very know, but I'll repeat, is friendsofsanpedrovalleypark.org. friendsofsanpedrovalleypark.org. And there's a lot up there for those who are interested in the park and activities and trails and so on and so forth. We have a terrific lecture ahead of us. And yes, it will be recorded and posted to the website in a week or two. We are indeed going on a tour of the heavens. Please write questions in the Q&A sections and comments in chat. Questions and comments will be taken at the end of the lecture. We'll handle as many as time permits. Adrian and I will be taking a summer break, and during that break, there will be 3 children's programs in the park. On July 2nd at 11 a.m., we'll have the Beetle Lady. Wild Things will be on Friday, August the 5th. I'm not sure what time. Wednesday, August the 10th at 11 a.m. with Wild Mind Science, which is from Half Moon Bay. And there are one of our regulars. So check our upcoming newsletter and the website for further details. I will return with more programming and more field trips in the fall. And today, I am truly honored, truly pleased to introduce Astronomer Bin Quack from the California Academy of Sciences in San Francisco. He is currently Assistant Director of Morrison Planetarium. He has taught astronomy courses at both the informal and college level. He is frequently interviewed on local media, explaining astronomical events, and writes daily skywatching tips that are distributed to approximately 30 newspapers across the country. He is the 2020 recipient of the Western Amateur Astronomers J. Bruce Blair Medal for Career Achievements in Amateur Astronomy. And please join me in welcoming Bing. Bing, take it away. It's your night.
Thank you, Mila. It's a pleasure to be with you. Good evening, everyone. I hope you are all well in your part of the universe. This is a very exciting time in astronomy, and in fact, things have been so fast moving. I haven't really known exactly how to approach this. So it'll be partly a tour of the night sky, but also partly a recap of some really exciting events that have been happening. I'll try to put them in the framework of looking at the night sky and where you might be able to see some of these phenomena that I'll talk about. Our first story is perhaps the biggest, and it is the picture of the supermassive black hole at the center of the Milky Way galaxy that was released just last month on May 12th. This was a big story. It's one that astronomers had anticipated for a couple of years. But first, I'm going to backtrack just a little bit and address the most obvious question, which is, what are black holes? What are these things? Well, black holes are the end stage in the life cycles of very massive stars. The simple version is that during a typical star's lifetime, the outward pressure of the energy it produces, which makes it want to expand, is balanced by the inward pull of gravity, which makes it want to collapse. In average stars like the sun, this equilibrium lasts for about 10 billion years. And we're about halfway through that. When the star inevitably runs out of fuel that it needs to create energy, then the gravity takes over and the star begins to collapse. Now, this part gets a bit complicated. There are several steps. There are a few transitional phases. But basically, depending on how massive the star is, in all cases, the final collapse is so catastrophic that the atomic structure breaks down, and subatomic particles of the matter that the star is made of are squished more tightly together than they would be under normal circumstances. A simple analogy is trying to stuff as many balloons as you can into a room. Now, only so many will fit, but there are still air spaces between the balloons. And on top of that, the balloons themselves are mostly empty space. If you let the air out of the balloons, then you can get a lot more into the room. So that's sort of like what happens at the end of a star's life. Stars the mass of the sun collapse into what are called white dwarfs. And these have the mass of the sun, pretty much, compressed down into something roughly the size of Earth, about a millionth of the original volume. Now, estimates vary because we don't have any white dwarf matter handy, but calculations suggest that a teaspoonful of white dwarf matter could weigh between 5 to 15 tons. Now, here's an image of the sun and the Earth side by side for comparison's sake, just so you understand what kind of scale we're talking about. Can you see the sun? Okay, now can you see the Earth? Earth is the tiny dot just to the left of the sun, right there. So you've got all this matter in the sun being squished down into something the size of the Earth, 1/1,000,000th the volume. All right. Now, there are two famous examples of white dwarfs in the winter sky, which we can't see right now because it's not winter. The sun is in that same part of the sky. But if we could see these particular stars, they'd be found orbiting two of the brightest stars in the winter hexagon, which is a very prominent shape in the wintertime sky, made up of the brightest stars in 6 different constellations. 2 of the brightest are Sirius, the brightest star in the entire nighttime sky, in Canis Major, the big dog, and Procyon in Canis Minor, the little dog. These are the 2 hunting dogs that accompany Orion the hunter, which is known as this large hourglass figure of stars, which is squaring off against Taurus the bull. So those are the prominent wintertime constellations where we find these white dwarfs. Now, here's an image of, I'll start with Sirius right here. And there's a photograph of Sirius, which is a bright star in Canis Major. Can you see the white dwarf, which is called Sirius B? Now, Sirius is also known as the dog star. It's the brightest star in the constellation of the big dog. So Sirius B has been dubbed the pup. So can you see it now? I've got these indicated for you. Sirius A, the star itself, the brightest star in the nighttime sky, has this tiny, tiny, tiny companion, the white dwarf, Sirius B. Now, about 5 billion years from now, after the sun goes through a transitional swelling into a red giant, it will eventually shrink down to a white dwarf, like Sirius B. It just doesn't have enough mass for the processes to occur that cause supernova explosions or create black holes. So the sun is never going to blow up. It's never going to turn into a black hole. It'll just shrink down into this tiny, tiny, tiny white dwarf. All right. So here's an image of Procyon and its white dwarf. Now, this is a little more difficult to see. Procyon is labeled right here. And Procyon B, the white dwarf, is this tiny faint dot in the glare marked by these little hash marks. You see that? So that's another white dwarf, 11 light years away. Sirius B, orbiting Sirius, is about 8 light years away. So that's how far away these objects are. Now, stars up to about 3 times the mass of the sun collapse down even smaller than white dwarfs. They turn into what are called neutron stars. And they have about 3 times the mass of the sun, squished down to as small as 10 kilometers, or about the size of a city like San Francisco. A teaspoonful of neutron star matter is calculated to weigh about as much as Mount Everest, or about 10 million tons. An example of a neutron star is also in the winter sky. Again, we can't see it right now because the sun is in that same part of the sky, washing everything out with its glare. But later on in the year, as we get toward winter, when you look up toward the winter hexagon and you see Orion and Canis Major and Canis Minor, and then Taurus the bull, right at the tip of one of the horns of Taurus is the tip of the horn is marked by a star called Tianguan. Right, that's the southern horn of Taurus the bull. The star was only just officially named in 2016, although its designation in the traditional Greco-Latin naming system is Zeta Tauri, Many amateur astronomers prefer to use its ancient Babylonian name, which is Shurnarkabtisha Shutu. It's a long name for a star in any language, one of the longest, and astronomers, amateur astronomers just love to say it because it's so long. It's a lot of fun to say. But 1 degree away from the star is an object known to astronomers as M1, or the Crab Nebula. Now, this is visible in a medium-sized telescope. It's a faint, fuzzy smudge of light, but it's a supernova remnant. It's what's left of a star after it blows off most of its mass in a tremendous explosion called a supernova. The collapsed core of the star at the very center of this cloud, which is about 10 light years across, this collapsed star is the Neutron Star. It has a twisted, contorted magnetic field that interacts with matter swirling around it, and it shoots out energy in jets, which is a common behavior that we see in black holes. So we have neutron stars and black holes which shoot out jets from their poles. This object, the Crab Nebula, is 6,500 light years away. So it's so far away that its light takes 6,500 years to reach us. Just like earlier I said, Sirius is 8 light years away. Its light takes 8 years to reach us. Procyon is 11 light years away. Its light takes 11 years to reach us. And so the light from the Crab Nebula takes 6,500 years to reach us here on Earth. Now, the term black hole wasn't used until 1967, but the concept of stars whose gravity is too strong even for light to escape was discussed as early as the late 1700s. Black holes are what stars up to about 20 times as massive as the sun collapse into. They compress down so much, and for their size are so dense and massive that their gravitational pull is inescapable for anything getting too close. Now, the distance that's considered too close is called the event horizon, and that varies with the mass of the black hole. Now, what you're looking at right now is not a black hole. It's a kinetic water sculpture in a museum in Italy, but whirlpools have often been used to represent black holes because the idea of something that pulls in everything around it and sucks it all up, or so it was thought, is such a weird thing to try to wrap your head around. The concept has changed recently, and nowadays the visualization of a black hole as used, as shown in the film Interstellar, is considered the most scientifically accurate model. So the first black hole was discovered in 1970, and it is in the sky tonight. We can see not the black hole, but we can see where it's located among the stars of the summer triangle. So let's look at the sky tonight of about, this is the sky of about midnight. Now, the summer triangle is formed high in the east by these 3 stars right here, which are each the brightest in its own separate constellation. The triangle itself is what's called an asterism, which is a simple shape made of bright stars that's easy to identify. So here's the summer triangle. And the stars that form it they belong to Lyra the harp, Aquila the eagle, and Cygnus the swan. We want to look at Cygnus the swan, this constellation. So these stars really do look something like, they suggest the shape of a swan with outstretched wings. Sometimes it's also called the Northern Cross. But right in the middle of the neck of the swan is this star right here called Eta Cygni. Now, with telescopes, astronomers look at Eta Cygni, or near Eta Cygni, and they can see this beautiful pinkish cloud of dust and gas called the Tulip Nebula. Does it look kind of like a tulip to you? Maybe, maybe not. But we have other exposures of this. This is an old picture when film was more sensitive to red lights. And now we have digital imagery, which can show us a lot more color and a lot more detail. So here's a more modern picture of the Tulip Nebula. And just off the top of the nebula, right here, is a feature which you might just be able to make up, to make out here. This curved structure here is the bow shock from jets that are being emitted by a black hole that has about 20 times the mass of the sun. It's orbiting this star right here, the brighter of these two stars that are close together. So it's orbiting this star, and it's called Cygnus X1. It was called that because it's in the constellation Cygnus, and it was the first source, very powerful source of X-rays that was discovered in that constellation. Cygnus X1 orbits the star HDE 226868. I wish they would find a better name for it, but that's the catalog name that astronomers use. And as it does, it's close enough so that its gravity attracts matter from the star, gathers it into what's called an accretion disk. Right here, this is the star itself, and the matter goes swirling toward the black hole, forming this accretion disk. As it moves faster and faster, the farther and closer in it goes, it heats up, gives off a tremendous amount of X-rays. That's why it's called Cygnus X1, giving off those X-rays. And the interaction of the matter with the magnetic field around the black hole shoots out jets just like a pulsar does, a neutron star. So that's what's going on here with this particular pair, the star HDE 226868 and Cygnus X1. Just before the matter disappears past the event horizon, that interaction is what shoots out the jets of material, and that's why we can still detect them and the X-rays given off by the material in the accretion disk. But in this lovely shot right here, you can see the star and the bow shock right there. And that's caused by the jet of material being given off, slamming into the interstellar matter that's between the stars here and forming this beautiful bow shock. We don't see one on the other side, but this side here is very, very obvious. So that's a beautiful, beautiful image of the effect of a black hole on the space around it. Now that's one kind of black hole. That's what's called a stellar black hole, but it's not the kind of black hole that was imaged at the center of the galaxy. That is called a supermassive black hole, and how supermassive black holes form and how they get to be so big is, to put it politely, it's open to research, which is another way for astronomers to say, I don't know. It seems that almost every large galaxy has a supermassive black hole at its center. And supermassive means just what that name implies, something that's more than just massive, but supermassive. And we'll see how massive this object is in just a minute. The supermassive black hole at the center of the Milky Way is just below the horizon at nightfall. So again, we're looking at the sky 1 hour after sunset. The glow of twilight is just fading in the northwest. The moon is beginning to rise in the southeast. We'll have to wait a little bit for that part of the sky to rise just a little higher. So at about midnight or so, we'll be able to see that part of the sky well. Of course, the moon itself is you can't miss it. It's almost full. So that means it's a little bright in that part of the sky. It washes out our view of many faint objects in the same region, including the center of the galaxy, which is not very far away, just a few degrees away, marked by GC, Galactic Center. So we have an advantage with the software like the one that I'm using right now. We can turn the moon off so that its glare doesn't get in the way of things. And that part of the sky becomes more visible, although it's still low in the south. It's within the stars of the constellation Sagittarius, the Archer. And so the object at the center of the galaxy is called Sagittarius A. It's in that constellation Sagittarius, and it's the brightest radio source in Sagittarius, so A. That has been shortened to Sagittarius A star. The asterisk is used in physics to denote something exciting in the notes that the physicists write. And so Sagittarius A star is the name of the supermassive black hole at the center of the galaxy. That's been shortened nowadays to Sag A star, which is easier than saying Sagittarius A asterisk. Observations of star motions over 10 years' time indicate that the stars are orbiting something that has a mass in the neighborhood of about 3 million suns. Now that's been updated. It's been refined to about 4.5 million suns. In particular, astronomers look at a couple of nearby stars which really whip around the star, and this is over 10 years' time. So that's what's going on. And they've calculated that this is because of the gravity of something that has 4.5 million times the mass of the sun. Now remember, a stellar black hole can have 10, 20 times the mass of the sun. So a supermassive black hole really is supermassive, 4.5 million times the mass of the sun. Sagittarius A, or Sag A star, is 27,000 light years away at the center of the galaxy. We're off about a third of the way from the center. So it's toward the direction of a lot of dust found along the galactic plane, and that dust gets in the way. To see through the dust, astronomers had to use a telescope the size of the Earth. That's the way the math works out. And by using a technique called interferometry, they were able to network 8 different telescopes around the world to simulate a telescope the size of the Earth. They called it the Event Horizon Telescope. And when they turned it toward the center of the galaxy, this is what they saw. That bright ring is the energy being given off by material swirling around the black hole, the supermassive black hole. The dark shadow at the very center is the event horizon, from which nothing is being emitted. And the weird thing here is that no matter what direction you observe this object from, you would see the same thing, a bright donut with a dark center. That's the weird thing about black holes and the way they affect light around them. Now, if this image looks familiar, it should, because a few years ago, in 2019, astronomers released another image of a different supermassive black hole at the center of another galaxy, which is 55 million light years away. That galaxy is called M87 in the constellation Virgo the Maiden, and it was already known to have a very active center. It's a large, what's called an elliptical galaxy, a large spherical blob of stars, not a spiral disk like the Milky Way. But we knew that it has a very active center with a jet shooting out from it. So at the same time the Event Horizon Telescope was imaging Sag A star, they were also imaging the center of M87. And images of the two look very similar. The difference, though, is that M87 star is about 1,700 times larger than Sag A star. It's a lot bigger than the supermassive black hole at the center of the Milky Way. And its mass is quite a bit bigger. Sag A star, again, about 4.5 million times the mass of the sun. M87 star has a mass about 6.5 billion times the mass of the sun. So this is supermassive, even for a supermassive black hole. So it was actually harder to image than Sag A star, even though Sag A star is the closer one. And the reason for that is that Sag A star is so much smaller, the light trapped in orbit around it can circle around in a much shorter time, while it would take much longer to orbit around M87 star. So while M87 star is politely sitting still, posing for the picture, Sag A star is like an excited puppy that's all over the place, and so it photographs as a blur. Here are some comparisons of M87 star. This is, again, the black hole at the center of M87, compared to the size, roughly, of our own solar system, that little circle there. And then we compare the size of Sag A star, the supermassive black hole at the center of the Milky Way, to, well, the orbit of Mercury. So Sag A star could fit inside the orbit of Mercury, but our solar system would fit inside the event horizon of M87 star. So there's a huge difference in sizes between these two objects. Again, the difference being about 1,700 times. If we compared them side by side, we'd have to reduce the size of Sag A star to about 1 pixel. And even that would be too big to compare with the image that we see here of M87 star. So those are 2 images of the supermassive black holes that we see in the centers of 2 galaxies. And this is a really remarkable achievement. For one thing, being able to photograph something 55 million light years away, and then looking at our own Milky Way, being able to photograph through all that dust and other material, being able to photograph an active black hole that's so close to us. So that is one of the big stories of just the past month or so. The next story is one that hasn't really happened yet. And that is the release of the first images from the James Webb Space Telescope. That is coming up. It's on the calendar. Now, James Webb is the follow-up to the Spitzer Space Telescope, which operated from 2003 to 2020. It's the largest, most complicated space telescope ever built, and it's about the size of a tennis court. Here it is next to the telescope team, and this big sunshade down here at the bottom, made of 5 layers of material called Kapton, something like mylar. That's about the size of a tennis court. So very, very big instrument. The main mirror is much larger than those of either Spitzer or even the Hubble Space Telescope. Some people were calling it the successor to Hubble, but that's not quite the case, because it's not going to observe in the same part of the spectrum that Hubble uses. Hubble looked at the near infrared and optical, but Spitzer and Webb are observing in infrared or heat, and that's what Webb will observe. Spitzer did this for 17 years, and by doing so, it could detect structures that aren't visible to our eyes. It detected the heat of newborn stars and planets that are still hidden behind clouds of dust. It could also pick out particular molecules that have very distinctive infrared signatures, such as carbon dioxide, carbon monoxide, methane, and water. And by honing their ability to work in the infrared region for the time that the Spitzer was in operation, astronomers got great practice for what they expect to do with Webb. Now, Webb, again, is expected to observe in infrared. It's expected to operate for about 20 years with about 1,000 times the sensitivity of Spitzer and about 100 times the power of Hubble. Just for comparison, here are some images from Hubble taken in optical wavelengths of various nebulae. And then we'll compare those with infrared views of the same objects. Same things, they're not going to move out of the way, same scale, but look what the infrared view shows. Look how many more stars are visible behind all that dust and gas. And that's what infrared shows you. So that's the sort of thing that astronomers hope to be able to view with the James Webb Telescope. Now, the trick is, though, the James Webb Telescope is not going to be orbiting the Earth. Here's another comparison between Spitzer and Webb. So Webb is going to be about 1,000 times more sensitive than Spitzer. But Webb is not going to be orbiting Earth where astronauts can get to it to fix something in case it malfunctions, like we could with Hubble. Instead, it's going to be operating about 1 million miles farther out from the sun at a place called the Lagrange point number 2 around Earth. We can't get there. It's 1 million miles away. We've been to the moon, but that's only a quarter of the distance to L2. So if something goes wrong, we can't do anything about it. The telescope had to be folded up so it would fit into the rocket for launch. And after it was shot into space, it took a month to get to where it needed to be, during which time it slowly unfolded little by little. And with about 300 potential points of failure, engineers had to do this very slowly, very carefully, bit by bit. Fortunately, everything went perfectly. In fact, the process went so well that operators say the telescope should meet, if not exceed, all expectations. So now it's out where it needs to be. They've finished aligning the mirror, which is made up of these 18 different segments. It's 21 feet across. They had to be aligned to a tolerance of a fraction of a human hair so that all the mirrors can work together as a single precisely curved surface, sort of like the way the observatories of the Event Horizon Telescope work together to operate as a much larger telescope the size of Earth. And although we've already seen some test images like this one, which was a star used for aligning the mirrors, NASA's finally announced that the first science images from Webb will be released on July 12th, 1 month from now, 28 days from now, in a joint press conference by NASA, the European Space Agency, the Canadian Space Agency, and the Space Telescope Science Institute. So 28 days from now, on July 12th, we'll see the first real science images from the Webb Space Telescope, if all goes well and if nothing happens in the meantime. And we've seen a couple of headlines that have been very sensationalized and very alarming, claiming that the telescope has been hit by a meteoroid, which it was, a micrometeoroid, a tiny particle of matter smaller than a grain of sand. It's being a bit overblown for drama's sake, I think. The impact wasn't unexpected because our spacecraft have been hit by micrometeoroids before. So here are some shots from the International Space Station. And here you can see a little hole in one of the solar arrays, another couple of holes here, a couple of dings. There's one in the mechanical arm that they use to manipulate things, another ding in one of the solar panels. So this sort of thing was expected. In fact, James Webb has already been hit about 4 times by micrometeoroids. So this is nothing that was not expected. The particle itself was smaller than a grain of sand. It was traveling very fast, but the effect on Webb's performance was marginally detectable. Scientists don't expect any negative effect from this, so don't panic. Because if you do, you might miss something that's going on in the morning sky right now. Unfortunately, the best part is yet to come. However, what's going on is being mislabeled as an alignment, which is not. That's a misuse of the term. There's no true alignment going on, as if the planets are all getting into a single file line like well-behaved school kids. The reality is that, like real kids, they're all over the place. Some are close to us, some are far away, some are going to the left, some are going to the right. The semblance of a line is simply due to the fact that we're looking along the same plane on which they're located. Actually, the planets are spread out quite a bit. And it's a beautiful arrangement, or you can call it a distribution. It's okay to even call it a line as seen from Earth, but it's just not an alignment. So what's going on? Let's look at tomorrow morning sky. About an hour before sunrise. And we already have 4 of the 5 planets you can see without a telescope visible above the horizon. And we've also got the moon just entering that same part of the sky, just approaching. In the next week or so, the moon will slowly move along this procession. It'll pass each one of these planets. So we've got the moon, Saturn, Jupiter, Mars, Venus. Mercury is just below the horizon. It'll come up in about another week or so. But in the next few mornings, the moon will slowly move toward that line. And on the 18th, it'll pass Saturn. Let a few more mornings pass. And on the 21st, the moon will pass near Jupiter. It'll pass Mars on the 22nd. And then on the 23rd through the 25th, it moves lower and takes a place between Mars and Venus. So it'll substitute for the Earth. And at that time, Mercury finally peaks up out of the morning twilight, becomes visible. But look at the way the planets are stretched out, and pay particular attention to the order. We've got Mercury, then Venus, and the moon, then Mars, Jupiter, and Saturn, all arranged in order of their distance from the sun, just the way we learned in school. So that's an interesting thing to see. And for the next couple of mornings after that, the moon is going to move even farther down. It'll pass Venus on the morning of the 26th and pass close to Mercury on the 27th, although it's going to be pretty close to the glow of sunrise at that time. And might be a little harder to see. It's slowly moving back toward the sun and is gradually going to disappear from view. One more image that I'd like to show share with you is from Saturday's astronomy picture of the day. Let's see if I can get it up right here. This shows a beautiful wide-angle view of the Milky Way. This was taken by a photographer in Portugal. This is something not many of us get to see because of light pollution or the glow of city lights. I want to encourage you all to go out and enjoy the night sky if you can. Get away from bright lights and look up and appreciate the universe around us. Look at the planets in the morning sky. Be on the lookout for meteors as they streak against the stars. Watch the full moon rise over the horizon. These are sights that have filled the human imagination with wonder for thousands of years. And all you have to do to share that sense of wonder is look up into the sky. And what I'd like to share with you as well are a few of the resources that I used to prepare this presentation. Hopefully they can be starting points for your own exploration of the sky. The one that I just used is from a site called Astronomy Picture of the Day, and there's the URL there at the very bottom. This is, it's a NASA sponsored site, and every day there's a brand new picture of something astronomical. And many of these are just gorgeous, gorgeous shots, like this shot of the Milky Way. Another good resource, especially for beginners, is the website of the Astronomical League. And there's a section there where they have something called Navigating the Night Sky, where they have a downloadable map of the night sky for each month. So that also points out binocular targets, interesting things, highlights of that sky, and it'll help you learn constellations and asterisms, which are easier to learn than constellations. Another one, especially if you have an amateur astronomy club near you, look them up. This is the website of the San Francisco Amateur Astronomers. And many amateur astronomy clubs are very similar. They occasionally host what are called star parties, which are viewing sessions where they get their telescopes out, and they love showing their telescopes off to the public. And so you can look at things, and the SFAA in particular has occasional star parties. And now that we're gradually moving out of the pandemic, they may start to have public star parties again in certain areas. And so keep an eye out for astronomy clubs in your area. There's one in San Mateo. There are others in the San Jose area. There's certainly one in the East Bay, the East Bay Astronomical Society. So there are lots of amateur astronomy clubs all over. And let's see, one more here. A website called Stellarium.org is where I got a lot of the star maps that I used in this presentation. And it's a very accurate planetarium simulator where you can see what the sky looks like. You can even simulate eclipses. It's frequently updated. It's an open source planetarium program for your computer, and it's free. You can either download it, load it up on your computer. There's a version that's an app you can put on your mobile phone. If you don't want to download anything at all, there's a version on the website that you can use. So it's an excellent resource. And there are lots of other similar programs all over the web. So this is what I did with Stellarium. It also has a section that talks about satellites. So it can simulate the passage of satellites across the night sky. So it's a great resource for looking that up. That's the material that I had for this presentation. If there are any questions, I'm happy to try to answer any of them, those that I can. And if I can, let's see, I guess I can stop sharing here and go back to full screen. If there are any questions, I'd love to hear what you got.
Let's see. I think we have to give folks a chance to formulate some questions.
And that's fine. There are always really, really interesting things to discuss and look at in the sky. There are lots of events in the space program going on right now. We're about to launch 2 giant rockets in the next couple of months. NASA is testing these out for its Artemis program. Is that my cat? No, that's not. That's not my cat. That is a famous cat who I think is no longer with us. He is Hamilton the hipster cat who lived in San Jose, and he had such a beautiful mustache. He was really famous for it. Barbara, thank you. Susan, thank you very much.
Let's see. From Paul, we have, do you have any favorite sci-fi movies or TV shows, ones that represent the reality of space?
Movies that come close, because movies are basically fiction. But some really good movies, Paul, that make use of astronomical concepts. My all-time favorite is 2001. There's also Interstellar. There's Contact, all based on solid science. Television shows I haven't been able to watch too much of because now it's subscription TV, so I don't have Netflix or Disney or some of those. But I hear that The Expanse is based on pretty solid astronomy, although I haven't seen it yet. Those are some of the films and TV programs that I'm aware of that come first and foremost to my mind. I see Patty has a question. Where's the best place near the Bay Area to see the Milky Way? Well, it's funny you should ask that, because back in 1989, right after the Loma Prieta quake, when all the power went out in San Francisco, that night I saw the Milky Way from San Francisco. But that was under a very unusual circumstance. On another occasion, I was in the Botanical Garden in San Francisco in the California section, the California Garden there. And it's so shielded by all the trees, I could see the Milky Way from there. So if you go to the right spot, if you go to the right spot, you might be able to find an area shielded enough so you can see the Milky Way. To really see it well, you have to get away from city lights. You really have to get away from the glow of light pollution, which means going out maybe as far as Mount Diablo or farther down the peninsula or up around Mount Tam, where you can at least get away from city lights and maybe shield yourself, courtesy of a nearby tree line. There's an observatory in Sonoma called the Robert Ferguson Observatory, which is at Sugarloaf Ridge State Park. They've got a great view, and it's a great observatory facility as well. So you might want to consider a few places like that. Charlene asks, which is the best meteor shower this summer? Usually in the summertime, people plan for the Perseid meteors in mid-August. It peaks on August 12th. However, this year, the Perseid peak comes very close to a full moon, and the light of a full moon can obliterate many of the faint meteors. But 2 weeks before that, at the end of July, there's another meteor shower, which it's not a bad one, and it peaks at the time of a new moon. So that shower near the end of July, it might average about 30 meteors per hour, 20 or 30 per hour. So that is a good one for the summertime because of the phase of the moon. You've got to make sure that the light of the moon is not going to wipe out the meteors that you want to see. So plan for that, and I forget which one it's called. It's one of the Aquarids. I think it's the Eta Aquarid meteor shower in late July. And I see another question here from Monica. Which phone app do you recommend for viewing the night sky? There are some really good phone apps. A lot of them are free. One that, Stellarium has a version that is mobile friendly. So you can download that and put it on your phone. Another app is, let's see, there are some that I got that I did have to pay for, but not much, like $1, a couple of dollars. One is called Pocket Universe. Another is called Go Sky. There's Sky View, Sky Guide. So those are a couple of pretty good programs, and they all do basically the same thing. They show you the constellations. Some of them automatically bring up the interpretation of the constellation when you point the camera toward it, and a lot of these work through your camera as well. So when you point the camera up to look at a particular constellation, it'll identify the constellation. So there are lots of really good apps. Joyce, for amateur stargazers, what kind of inexpensive equipment do you recommend? Well, you know, you can't go wrong with a good pair of binoculars. You may not think it's as powerful as a telescope, doesn't have as big a lens as a telescope, but you can still see a lot with a good pair of binoculars. And it's a good way to get into observing gently without spending too much money. With a good pair of binoculars, you can see the moons of Jupiter. Now, you might have to mount the binoculars on a tripod so it's rock steady, but you know, the jiggling of your hands as you try to hold the binoculars up might make the tiny, tiny images of Jupiter's moons hard to see. But you can certainly make out the disk of Jupiter. When Venus is at its brightest, you can see the disk, or you can see the crescent of Venus in binoculars. You can see nebulae. Some star clusters actually look better in binoculars than with a telescope because they've got a wider field of view. For the Pleiades, or also known as the Seven Sisters, you can see the entire cluster. Whereas through a telescope, you only see a small part of it, and you see a few of the stars, but there are a lot more beyond that. So there are some things that you can see really, really well with binoculars. The Andromeda Galaxy, visible in the fall sky. I think it's better through binoculars than through a telescope, because you tend to see a smaller, more concentrated image, and so it stands out more easily. So there are a number of good telescopes you can look at, and you can do a Google search, and you can even use the search, use the phrase, good telescopes under $200, and it'll look for that and give you a list. But I would think about a good pair of binoculars, because not only can you use them for observing the night sky, you can also use them for observing nature. You can use them for bird watching. You can use them for sports and lots of other events as well. So that's a really good way to gently ease yourself into observing the night sky. Robert, what is your wallpaper? Oh, remember earlier I talked about Cygnus X1 and the Tulip Nebula. This is the Tulip Nebula right here behind me. And you can just make out the blue arc, which is that bow shock of the jet being shot out from Cygnus X1. So this is the Tulip Nebula in Cygnus the Swan. Any update on the dimness brightness of Betelgeuse? Now, that's an interesting story. A number of years ago, Betelgeuse is the shoulder of Orion, a bright red star, and it's easy to see. A couple of years ago, it started to dim, and astronomers weren't quite sure what was going on. Now, we know that Betelgeuse is a very old star. It's near the end of its main life. And some astronomers say that Betelgeuse is the type of star that could go supernova. It's massive enough, it could blow up as it approaches the end of its life. And at that time, a few years ago, as it started to dim, some people were speculating maybe it's getting ready to blow up. And then it started to brighten again. And what some astronomers think happened was that it was just being blocked by a cloud of dust orbiting around it. And that made it dim temporarily. And so it brightened again, and the astronomers said, okay, we got to fake it out. Well, recently, there's been another report that has begun to dim again. So maybe there's another cloud of dust getting in the way. Maybe it's the same cloud of dust. So we don't know. We need to study this situation a little more carefully. But good old Betelgeuse in Orion's shoulder, it started to dim, and then it brightened again, and now maybe it's beginning to dim again. So we'll have to keep our eye on that. Bing, hi Bing, great name. Is the Webb telescope moving in synchrony with Earth? Yes, because it's at L2, it's locked at that point and basically co-orbits with Earth. So Earth, the Sun, and the Moon, and L2 and Webb are always in line with each other. So as Earth orbits around, Webb is always going to stay in line a million miles farther out from the Sun than Earth. So you can actually see Webb with a moderate-sized telescope, but to see it, you have to follow it as it tracks across the zodiac, which is the belt of constellations that defines the plane of our solar system. So it will move against the constellations over time. So it does track with the Earth. And Monica, Skyview. Good. Okay. You've used Skyview. There are other programs. So look at some of the others. Patty, are you familiar with any astronomy tours, local or other tours? Well, the facility that I mentioned earlier, Robert Ferguson Observatory in Sonoma, they do have tours of the facility. As a matter of fact, they have the largest publicly accessible telescope in California. They have a 30-inch reflector. Lick Observatory has a 36-inch telescope, but it's not available. It's used for research purposes. But Robert Ferguson Observatory, excuse me, and their website is rfo.org. You can look them up, see when they have visiting hours. It's not one of your big stately big dome observatories. It's a series of sheds, but it's very well equipped, and the staff there are wonderful. They've got great volunteers there operating it. So look them up, rfo.org, Robert Ferguson Observatory. I don't know if there are any other questions here, Mila.
Well, let's see what's in the Q&A section. Are all of these?
Denis recommends H.A. Ray's The Stars, A New Way to See Them. It's an old book with a slightly different interpretation of the constellations, and it's a classic. If you aren't familiar with Harold Ray, isn't he also the creator of Curious George? I thought so. But he did a great book interpreting the constellations as well.
And then Jeanette is saying, what do you think the effects of humankind have been, as many of us no longer have access to a view of the night sky?
Oh my goodness. There was something I was going to mention in the talk, but I thought it was getting too technical and maybe a little too negative. Of course, I did mention light pollution earlier. It's all around us. There's not a place on Earth that light pollution does not affect. There, you can go up to the mountains or out to the high desert. There's still a little bit of sky glow that you can see. And the lights of civilization have gradually encroached more and more on our view of the night sky. That's why there are some areas that are being designated as dark sky sites. And people are trying to preserve that. Another concern for many astronomers is the number of satellites that are being launched into space. I mean, just a couple of years ago, there were only maybe 1,500, 2,000 satellites orbiting the Earth. And these are communication satellites, weather satellites, all sorts of things. Now we have companies that are launching these mega constellations of satellites. And one is plans to launch 40,000 satellites into orbit. Of the number of satellites orbiting Earth right now, which is now it's risen to about 4,500. More than half of those belong to one particular company because they've been launching satellites in batches of 50 or 60 a time, several times a month. And they're working up toward that number of 40,000. And there have been photographs printed. In fact, this morning's astronomy picture of the day. So you go back to that site that I mentioned earlier, APOD, we call it. This morning's astronomy picture of the day shows the traffic over 2 hours time over the photographer's location in Australia. And there are satellites all over. There are lines crisscrossing, and it looks like a collision of spider webs across the sky. And that's a concern for astronomers because their view of the sky is being blocked, being photobombed by a lot of these satellites. And for professional research astronomers who are working, there's a new observatory called the Vero Reuben Observatory down in Chile. It is a special type of observatory which is going to take wide-angle views, wide-angle surveys of the sky, covering the entire sky over just a couple of nights' time. And that data will be publicly available as soon as possible. But as they view the sky, they're going to be getting all these satellites crisscrossing their field of view. And that could be a problem for them, could be blocking some of what they want to see. Now, the one positive here, I think, is that satellites are visible only because they reflect the light of the sun. So they're visible just after sunset or just before sunrise. In the middle of the night, they're not as visible. So there's that. But satellite manufacturers are gradually working with astronomers, trying to mitigate the effects of the satellites, trying to figure out ways to make them less reflective or orient them in a certain way that doesn't reflect as much light. But there's a lot of traffic up there. And there are 2 space stations in operation right now. Both of them have had to maneuver out of the way of incoming satellites. Now, there was no danger of an actual collision, but it came close enough for them to want to know where it is. So there's a lot going on up there, and there are more space stations being planned for the future. So that's another effect of our modern technology that is having an effect on the sky. So
Can the satellite, I'm sorry, Bing, but can the satellites actually start colliding with one another? I mean, it seems as though
yes, Mila,
and
that has happened. Satellites have collided with each other. There are so many up there now. Now, a lot of them are in different orbital altitudes, so they should miss each other. But there have been collisions, and when things collide and smash together, they break, and the little pieces become other little satellites that are whizzing around Earth at 17,000 miles an hour. So yeah, we need to do something to clean up orbital space.
It seems as though the traffic jam up there.
Yeah, there are some companies that are actually trying to develop technologies and strategies for cleaning up at least the used, obsolete satellites that are no longer in operation. And I wish them luck. That's a big job.
And what do you expect? Do you have any expectations about what you'll see in with the Webb telescope?
What is the Webb going to see? I don't know, and a lot of astronomers don't know, and they're not willing to speculate. But we should get a clearer view of anything that Hubble and Spitzer saw. So we'll see more detail. We should be able to see farther into the universe and therefore farther back in time, closer to the time of the Big Bang, to see what the early universe may have been like, and what the conditions there may have been. Impact of the pillars of creation, Hubble ultra deep space. Okay, Robert, I'm not quite sure what you're talking about. The pillars of creation is the name given to a picture that the Hubble Space Telescope took of a section of a nebula called M16, the Eagle Nebula. And it took just of these large pillars of gas where stars are forming. And each of these pillars was about a light year long. And it was very dramatic. And it was one of the pictures that I showed you earlier. And we transitioned from that to an infrared view, and you just saw thousands of stars suddenly appear in the background. So that's one of the images that I showed you. Hubble is on, it's kind of on borrowed time right now. It's hopefully got a few more years left in it, but it's getting old. And some astronomers are thinking that maybe what Webb is able to start observing can substitute for what Hubble was doing, although it's seeing in a different region of the spectrum.
Well, what ages, Bing, what ages a telescope up there? I mean, if it's up there for a year or 5 or 10 or 15, what makes it age?
What ages an instrument like the Hubble telescope? Well, you've got the effect of solar radiation. You've got, as I showed you, micrometeoroid impacts. We've got, and the components just begin to wear down too, and a couple of them have. So the telescope orients itself with gyroscopes, and if the gyroscopes gradually wear out, they can stop functioning as well. So it does have a limited lifetime.
Huh.
Robert asks another question about the total lunar eclipse. That's from Vicky. I didn't, because it was very cloudy from where I tried to observe in San Francisco. And for this particular lunar eclipse, it was already in progress as the moon rose. So it would have been difficult to see at moonrise because the moon was already pretty dark. And then the clouds came in anyway, so that blocked my view a bit. I wasn't able to see it, but a number of other people farther out to the east did, and there's some really great pictures of it. Okay, I don't know if there are any others. Robert had another question, something about the Hubble ultra deep field. I assume that's what you're asking about. Hubble was used to take a number of pictures of different random parts of the sky where astronomers did not expect to see very much, and it took long exposures, maybe 10 or 11 days, something like that. And in almost all of these, in the very tiny part of the sky that it looked at, it observed 3 to 10,000 galaxies. So since these were random parts of the sky, it would seem to suggest that every direction you look, you will see a density of about 3,000 galaxies in a little space about the size of a grain of sand held at arm's length. So how many galaxies then does it take to cover the entire sky? These were unknown galaxies, and it was an amazing sequence of photographs that was taken. But those were the Hubble Deep Field, then the Hubble Ultra Deep Field, and then they started running out of names to call them. But there are 4 or 5 of these very long exposure images of a tiny part of the sky, which uncovered about 10,000 galaxies. Really amazing shots. So great images.
My question has to do if you still have time, just with the whole idea of how the telescope opens up. I mean, it has to be so small and compact. They've developed a system, obviously, that seems to work quite well, where once it's up there, bit by bit, this huge thing opens up gradually into all computer controlled. How in the world do they get something that large, so compact, and to get it to open up to actually and function?
Well, that's a great question. It's a real engineering challenge. The Webb telescope was designed to be foldable, so they had to start from there. It had to fit inside the nose cone of the launch rocket, and so they designed the mirror in segments so that it could fold along the joins of a couple of those segments. Then the antenna also was collapsible. The sunshade itself was really tricky, but it basically pulled out very slowly, like a window shade. But there are 5 layers, so they did this very slowly. They didn't want to rush anything. That's why it took a couple of weeks for the full deployment, the full unfolding of the telescope. And they thought it through so well, and really planned it out so carefully that it just went smooth as silk. And it went so well that things went better than they expected. So, here's okay. I see a couple of other questions here. Yeah, I don't know what to expect from Webb. Black holes at the center of galaxies is the force accountable for the motion of planetary bodies in our solar system. The supermassive black hole at the center of the Milky Way is not affecting the motion of the planets in our solar system. We're 27,000 light years away. So the pull of gravity is extremely weak across that distance. And don't go thinking that black holes are these cosmic vacuum cleaners that are just going to suck everything up eventually and everything's going to disappear into them. They don't do that. It is effective only across the distance that the original star would be. The thing about a black hole is you can get so close to the center of mass that the gravity, what's called the gravity gradient, is really, really strong. Usually, before the object collapses into something as dense as a black hole, you can't get that close for that to happen. If the sun, and it won't, but if the sun were to suddenly turn into a black hole, the planets wouldn't suddenly go sucked into the center of the solar system. They would just keep on orbiting the way they are now. So no, the gravity of the supermassive black hole at the center of our galaxy is not affecting the motion of our planets. Good question, though, Jeanette. Let's see. Any others? Okay, space junk. We talked about space junk. Hubble Ultra Deep's image pillars of creation. Okay, I think, is that it?
It looks like it.
Okay, well.
Well, all right.
Excellent questions. I hope you keep asking questions. That's why astronomers and scientists do what they do, because they're just asking questions. And I hope this has been entertaining for you. I had fun, and
Well, thank you so much for agreeing to come and writing this special program just for us, and having to do several almost rewrites of it in order to conform to the things that are happening.
It's a sign of the exciting times that we're in, because things are happening so fast and are so dynamic. You have to change something every now and then, and make a quick adjustment. So I hope I put it together for you, and I hope it helps you understand a little bit more about what's going on, and encourages you to keep asking questions and look things up.
Well, we certainly appreciate your coming and discussing all of this, and we hope to have you back, hopefully.
Sure.
Soon.
I'd love to.
It's a long time between all the cancellations with PG&E and fires and everything else.
That's true.
We haven't seen you in so long, and we've missed you tremendously. So I thank you so much, and we all thank you for a tremendous presentation.
Well, thank you.
And Adrian right beside me is also trying to squeeze into the image, okay, which is, as we know today, sort of not quite the way it is usually, but we're doing the best we can with techie stuff today. And thank you all for joining us, and we will let Bing Quack have an evening now, and so we'll let him go so he can have dinner and enjoy the rest of his evening. And so thank you all for joining us. Thank you, Bing, again, and I hope to see you at somewhere at the Academy in the planetarium somewhere to run into you, hopefully.
Absolutely.
In the near future.
Sure.
All right. Take care and many thanks. Good night. Good night, everyone. Take care.
There was some delay.
Okay. What should I do here?
Just that,
Yeah.